Hello, friend. Thank you for finding your way here tonight. Some nights the universe feels closer than it should. Stars whisper secrets we've been waiting lifetimes to hear. And sometimes, after nearly a century of wondering, a frozen world at the edge of everything shows us something we never expected to see. A heart, made of ice, beating slowly across 5 billion kilometers of darkness. On July 14th, 2015, after traveling for 9.5 years through the silent void, a spacecraft no bigger than a grand piano flew past a world we thought we understood. What it saw changed everything. Not just what we knew about Pluto, but what we believed about the far edges of our solar system, about cold, about death, about worlds we'd written off as lifeless and forgotten. Pluto had been waiting. And when we finally arrived, it smiled back. Before we drift into this story together, if these quiet journeys through space bring you peace, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories told softly, and ring the little bell not for noise, but so the next quiet night can find you again. No pressure, just an invitation to wander with us whenever you're ready. Now, let's drift. Tonight we'll travel to the most distant world humanity has ever visited up close. A place so far away that sunlight racing at 186,000 miles per second takes over 5 hours to reach it. By the time the light touches Pluto's surface, it's 1,000 times dimmer than the sun you see from your window. Out there in the cold and the dark, Pluto orbits, alone, but not quite. For 85 years, we wondered what it looked like. We knew it was there. Clyde Tombaugh discovered it in 1930, a faint dot moving against the stars, barely visible even through the best telescopes of the time. He was 24 years old, working at Lowell Observatory in Arizona, comparing photographic plates night after night, searching for the mysterious Planet X that astronomers believed must exist beyond Neptune. And then, on February 18th, he found it. A tiny speck of light, shifting position over 6 days. The 9th planet. A world at the frozen edge of our solar family. For 76 years, Pluto held that title. Children grew up memorizing its name alongside Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. It felt right, complete. 9 planets each with its place, its story, its role in the cosmic architecture. But in 2006, something changed. The International Astronomical Union met in Prague and redefined what it means to be a planet. 3 criteria. It must orbit the sun, it must be massive enough to be rounded by its own gravity, and here's where Pluto stumbled. It must have cleared its orbit of other objects. Pluto hadn't cleared its orbit. It shares the Kuiper Belt with thousands of other icy bodies, some nearly as large as itself. And so, with a vote, Pluto was reclassified. No longer the 9th planet, now a dwarf planet. Many people felt betrayed, angry even. How could we demote a world that had been part of our mental map of the solar system for 3/4 of a century? Some scientists still debate the decision today. But here's the thing most people miss. The demotion wasn't an insult. It was an invitation to look closer. Because if Pluto wasn't alone out there, if it was part of a vast populated frontier we'd barely begun to explore, then maybe it wasn't an oddball after all. Maybe it was a guide, a first glimpse into an entirely new realm of our solar system, full of ancient frozen worlds that held secrets about how planets form, how solar systems evolve, how ice and rock and chemistry can create something extraordinary. And in 2006, just months after Pluto's reclassification, NASA launched New Horizons, a spacecraft built for one purpose: to visit Pluto, to see it up close, to answer the questions we'd been asking for nearly a century. What does it look like? What's it made of? Is it just a dead, icy rock tumbling through darkness? Or is there something more? The spacecraft was fast, the fastest object ever launched by humanity, at the time reaching speeds of over 36,000 miles per hour. Even at that speed, even with a perfect trajectory assisted by Jupiter's gravity, The journey took 9.5 years. Think about that for a moment. 9.5 years of silence, of waiting, of traveling through the dark alone with nothing but distant stars for company. The spacecraft passed Mars in 60 days. It passed Jupiter in 13 months. And then for the next 8 years, it flew through the outer solar system, where planets are separated by billions of miles, where space is so empty that if you could fit the entire solar system into a football stadium, Pluto would be a grain of sand on the 50-yard line, and Earth would be a pinhead near the goalpost. In those years, the team on Earth could only wait. They sent commands, they checked systems, they hoped the spacecraft wouldn't hit a piece of debris, wouldn't suffer a malfunction, wouldn't drift off course by even the tiniest fraction. At those distances, there's no room for error. If something goes wrong, by the time the signal reaches Earth, traveling at the speed of light, over 4.5 hours have passed. Another 4.5 hours for a response to reach back. 9 hours round trip. Enough time for a disaster to become irreversible. But New Horizons kept flying, quiet, steady, and full of purpose. And then, in early 2015, it began sending back the first images. Blurry at first, Pluto was still millions of miles away. A pale dot, slightly oblong, with hints of lighter and darker patches. The team squinted at their screens. They measured brightness. They tried to make sense of the patterns. And as the months passed, the images grew sharper. By June, Pluto began to resolve into something more than a dot. By early July, surface features became visible: mountains, plains, strange irregular patches of brightness. And then, on July 14th, 2015, New Horizons made its closest approach. It flew within 700-800 miles of Pluto's surface, closer than the distance from New York to Sydney. At that moment, traveling at 31,000 miles per hour, the spacecraft had just a few hours to gather as much data as possible. Every camera, every spectrometer, every sensor was working at full capacity, drinking in the light, reflected from a world no human had ever seen clearly. And what it saw, no one predicted. A heart. Right there in the southern hemisphere, stretching across 750 miles of Pluto's surface, a bright, smooth, almost perfectly heart-shaped region of ice. Scientists would later name it Tombaugh Regio, after the young astronomer who first discovered Pluto 85 years earlier. But that heart was more than just a beautiful accident of geology. It was young, impossibly young. Scientists study the age of planetary surfaces by counting craters. Every world in the solar system gets bombarded by asteroids, comets, and debris over billions of years. The more craters, the older the surface. Ancient terrains on the Moon, Mars, and Mercury are scarred with thousands upon thousands of impact craters, some overlapping, some eroded, but all testifying to the slow accumulation of cosmic violence over eons. Pluto's heart had almost no craters. That meant the surface was recent geologically speaking, perhaps only a few 100,000 years old, maybe even younger. On a world that's 4.5 billion years old, that's like finding fresh paint on an ancient ruin. Something was renewing the surface. Something was erasing the craters, smoothing the ice, reshaping the terrain. But Pluto is small, smaller than Earth's moon. It shouldn't have enough internal heat to drive geological activity. It's too far from the sun to receive meaningful warmth. Its core should have frozen solid billions of years ago. And yet, there it was. A heart that shouldn't exist on a world that shouldn't be alive. The images kept coming. As New Horizons sped past and began looking back, it captured Pluto in a thin crescent backlit by the distant sun. And there around the edges, scientists saw something else they didn't expect. A haze. Thin blue layered like Earth's atmosphere, seen from space but far more delicate. Pluto has an atmosphere. Not much of one, the surface pressure is about 100,000th of Earth's. But it's there held tenuously by Pluto's weak gravity constantly leaking into space, constantly replenished by nitrogen ice evaporating from the surface. That blue haze is made of Tholen's complex organic molecules formed when ultraviolet light from the sun breaks apart methane and nitrogen in the upper atmosphere. These molecules drift down, settling on the surface, staining the ice red and orange in some regions. It's the same chemistry that gives Titan Saturn's largest moon its orange color. Pluto wasn't dead. It was breathing, slowly, quietly, in its own frozen way. The temperature there is unimaginable. -223 degrees Celsius, -370 Fahrenheit. At those temperatures, nitrogen, the gas that makes up most of Earth's atmosphere, freezes solid. Carbon monoxide freezes. Methane freezes. Even the air you're breathing right now would turn to snow and fall silently to the ground. And yet on Pluto, that frozen nitrogen flows. It moves, it shifts, it convects like a lava lamp in extreme slow motion, driven by faint warmth from the planet's interior and the distant patient heat of the sun. This is the paradox of Pluto. A world so cold that it should be static, locked in place, geologically dead for billions of years. And yet, it moves. It changes. It surprises us. Many people, when they first heard Pluto had been demoted, felt a kind of sadness, as if we'd lost something, as if calling it a dwarf planet diminished its importance, its wonder, its place in our hearts. But New Horizons showed us the truth. Pluto didn't need our validation. It didn't need to be called a planet to be extraordinary. It simply was. And in being exactly what it is, small, distant, cold, and impossibly alive, it taught us something we keep forgetting, that the universe doesn't care about our categories. It doesn't care about our definitions. It simply exists in all its strange and beautiful complexity, waiting patiently for us to notice. Clyde Tombaugh, who discovered Pluto in 1930, passed away in 1997, 18 years before New Horizons launched. But the mission carried a small capsule containing some of his ashes, so that in a way he could complete the journey he began all those years ago. On July 14, 2015, those ashes flew past the world. He discovered finally seeing it up close, finally witnessing the heart he could never have imagined. And now, a decade later, New Horizons continues its journey. It has left Pluto far behind, flying deeper into the Kuiper Belt, into regions of space no human-made object has ever explored. The data it collected during that single day of closest approach, compressed, stored, transmitted slowly across billions of miles, took 16 months to fully download. 16 months of discoveries, of revelations, of learning that what we thought we knew was only the beginning. Pluto has 5 moons. Mountains made of water ice as hard as granite. A giant glacier that might still be moving today. Canyons, cliffs, and strange polygonal patterns that suggest convection cells beneath the surface churning like a pot of thick soup on the slowest simmer imaginable. Every image raised a dozen new questions. Every answer led to deeper mysteries. This is what exploration feels like. Not the neat, tidy conclusions we see in textbooks, but the messy, beautiful process of realizing how little we understood and how much more there is to discover. You don't need to remember every detail tonight. You don't need to hold on to the numbers, the dates, the technical terms. Just rest in the knowing that far beyond the light of our familiar sun, there's a small frozen world with a heart of ice quietly teaching us that distance doesn't mean lifeless and cold doesn't mean dead. That even at the edge of everything there's beauty, there's mystery, there's something worth the journey. And speaking of that journey, that heart of ice holds secrets deeper than anyone expected. Because when scientists looked closer at Tombaugh Regio, at the smooth plains inside that frozen heart, they realized they were looking at something that shouldn't be possible. A surface being renewed, reshaped, transformed by processes we're only beginning to understand. Let's drift a little deeper into that mystery. Inside that heart, there's a plane of ice so smooth, so perfectly flat, that it looks almost artificial, as if something or someone had carefully polished the surface, erasing every imperfection, every scar, every trace of the billions of years that Pluto has orbited the Sun. Scientists call it Sputnik Planitia, named after Sputnik 1, the first artificial satellite humanity ever launched into space back in 1957. It felt fitting somehow, a name that honored the beginning of the space age given to a place that represents what might be the strangest, most active surface in the outer solar system. Sputnik Planitia stretches across 1,000 kilometers, roughly the distance from New York to Florida. If you were standing at one edge, the horizon would curve away so gently that the far side would be invisible, lost beyond the limits of sight, even in Pluto's thin, hazy atmosphere. And across that entire expanse, there are almost no craters, not one or two. Not a few small impacts that happened recently, almost none at all. This is extraordinary. Everywhere else in the solar system's surfaces tell their age through scars. The moon's highlands are saturated with craters so many that new impacts simply overlap old ones, creating a chaotic landscape of circles within circles' walls, eroded by billions of years of micrometeorite bombardment and radiation. Mercury looks the same. Parts of Mars, the moons of Jupiter and Saturn, even Earth would look that way, if not for wind water and tectonic plates constantly reshaping the surface, hiding the evidence of ancient violence. But Sputnik Planitia is smooth, which means it's young, perhaps only 100,000 years old, maybe even less. On a world that has existed for 4.5 billion years, that's equivalent to a single second in a day. A fresh coat of paint on an ancient monument. A new page in a book written over eons. Something is renewing this surface. Something is filling in the craters, smoothing the ice, erasing the past, faster than the universe can write new scars. But what Pluto is small. It's about 2/3 the diameter of Earth's moon, with only about 1/6 the mass. Small worlds cool quickly. The heat from their formation, from the decay of radioactive elements deep inside, radiates away into space over hundreds of millions of years. Eventually, the interior solidifies. Everything stops. Volcanism ends. Tectonics cease. The world becomes geologically dead, a frozen museum of its own history. That's what should have happened to Pluto billions of years ago. Instead, Sputnik Planitia is moving. The surface isn't solid in the way we usually think of solid. Yes, it's frozen nitrogen ice locked at -223 degrees Celsius. But frozen doesn't always mean static, because even at those temperatures, ice can flow. Not like water, not like anything you'd recognize as fluid in everyday life. But over years, over centuries, over millennia, it moves. Imagine honey on a cold winter morning. It seems solid, almost glass-like. But if you leave it long enough, it will slowly flow, settling into new shapes, responding to gravity, to pressure, to temperature differences, too subtle to feel. Sputnik Planitia is like that. A glacier of nitrogen ice thick enough that its own weight causes the lower layers to deform, to creep, to convect. Convection. That's the key. You've seen convection before, even if you didn't know the name. When you heat a pot of water, the water at the bottom warms first. Warm water is less dense than cold water, so it rises. The cold water at the top sinks to replace it. This creates a cycle, a convection cell, where fluid continuously circulates driven by temperature differences. The same thing happens in Earth's mantle deep beneath the crust. Hot rock rises, cools, sinks, heats again, rises. This cycle drives plate tectonics, builds mountains, opens ocean basins, reshapes continents over millions of years. And it happens on Pluto. Not with rock, not with water. With frozen nitrogen. When scientists looked closely at Sputnik Planitia, they noticed patterns. The surface is divided into irregular polygons, cells roughly 10 to 40 kilometers across each outlined by shallow troughs. The cells look almost organic, like the pattern of mud drying in the sun, or the structure of a giraffe's skin. These polygons are convection cells. The nitrogen ice at the surface is exposed to space radiating heat away into the void. It cools, becomes denser, and slowly sinks. Meanwhile, warmer ice from deeper down, warmed by the faint residual heat from Pluto's interior, rises to replace it. This cycle takes somewhere between 500 to 1,000 and a million years to complete one full turn. That might sound slow, but in geological terms, it's astonishingly fast. It means that every square meter of Sputnik Planitia you see today will have sunk down, traveled through the depths of the ice sheet, and risen back to the surface within a time frame shorter than modern humans have existed on Earth. And as the ice convects, it erases craters. Any asteroid or comet fragment that strikes Sputnik Planitia makes a crater, yes. But that crater doesn't last. The ice around it fills in. The depression smooths it over. Within a few 100,000 years, a blink of an eye geologically, the crater is gone, forgotten, swallowed by the slow, patient churn of convection. This is why Sputnik Planitia looks so young. It's not that it hasn't been hit by debris, it has. But the evidence doesn't accumulate. The surface renews itself over and over, like skin healing, like a river smoothing stones, like time itself, erasing the past. But here's where it gets even stranger. Sputnik Planitia isn't just smooth, it's also shaped. The entire plane sits inside a massive basin, an impact crater so large that it warps the shape of Pluto itself. Scientists believe that billions of years ago, something big struck Pluto. Not a small asteroid, but a massive object, perhaps hundreds of kilometers across. The impact excavated an enormous cavity, removing rock and ice, leaving behind a depression that could swallow entire mountain ranges. Over time, that depression filled with nitrogen ice. And because nitrogen ice is less dense than water ice, and because Pluto's interior is mostly water ice and rock, the nitrogen-filled basin became lighter than the surrounding terrain. It floated in a sense. Not literally everything is solid after all, but gravitationally, it acted like a bubble of wood and water, creating an imbalance. And that imbalance had consequences. Pluto and its largest moon, Charon, are locked together in what's called tidal lock. They orbit each other, always showing the same face to one another, like two dancers frozen mid-step. But if one side of Pluto becomes lighter, if a massive basin fills with less dense ice, the whole system shifts. Pluto reorients itself so that the lighter side faces away from Charon toward empty space, seeking equilibrium. Sputnik Planitia sits almost exactly on the opposite side of Pluto, from Charon. That's not a coincidence. It's physics written across the surface of a frozen world. And there's another mystery hidden here. The nitrogen ice in Sputnik Planitia is pure. Not perfectly pure, there are traces of carbon monoxide, methane, small amounts of other frozen gases, but far purer than the ice elsewhere on Pluto. The surrounding terrain is stained red and orange with tholins, those complex organic molecules formed by sunlight, breaking apart methane in the atmosphere. But Sputnik Planitia is bright, clean, almost white in some regions. Why scientists suggest the convection itself might be the answer. As ice rises from below, it brings fresh, unstained material to the surface. The tholins don't have time to accumulate before the ice sinks again, carrying them back down into the depths. It's like a self-cleaning surface, constantly renewing itself, constantly washing away the stains of time. This challenges something many people believe about the outer solar system. We tend to think of places beyond Mars as cold, dead, unchanging. Frozen wastelands where nothing happens, where geology stopped billions of years ago, where time moves so slowly that visiting one century or another wouldn't make any visible difference. But Pluto proves that's wrong. Cold doesn't mean dead. Distance doesn't mean lifeless. Even at negative 223 degrees, even 5 billion kilometers from the sun, a world can move, can change, can surprise us with the complexity of its processes. Have you ever thought about what alive really means? We usually define it biologically, cells metabolism, reproduction. But there's a broader sense of aliveness that has nothing to do with DNA or chemistry. It's about response, about adaptation, about a system that maintains itself, that fights against entropy, that continues to exist, not through static rigidity, but through dynamic balance. In that sense, Sputnik Planitia is alive, not in the way a tree is alive or a bacterium, but in the way a river is alive, in the way weather is alive, a system driven by energy, by gradients, by the slow but persistent flow of matter-seeking equilibrium. And there's beauty in that. A different kind of beauty than we usually celebrate, but beauty nonetheless. The beauty of patient and human processes unfolding over time scales so vast that a human lifetime is barely a heartbeat. The beauty of nitrogen ice, colder than anything you've ever touched, flowing like honey through the depths of an alien plane, reshaping itself, endlessly erasing its own history, forgetting and renewing in equal measure. Some scientists wonder if Sputnik Planitia is still convecting today. The data from New Horizons suggests it is, but we only saw a snapshot a single day in the 4.5 billion year life of this world. It's like trying to understand a forest by looking at one photograph. You can see the trees, but you can't see them grow. You can see the stream, but you can't see the water move. To truly know if Sputnik Planitia is active right now, we'd need to go back, to watch it over years, over decades, to measure tiny changes in surface elevation, to track individual convection cells as they rise and fall, to witness the slow dance of ice in real time. Maybe someday we will. Maybe decades from now, another spacecraft will visit Pluto, equipped with better instruments, longer observation time, the ability to orbit rather than simply fly past. Maybe it will watch Sputnik Planitia long enough to see the ice move to confirm what the evidence strongly suggests. Or maybe we'll never know for certain. Maybe Pluto will keep its secrets a little longer, the way distant places often do, offering glimpses but never full disclosure, teaching us just enough to know how much we don't understand. There's something fitting about that, something right, because the universe doesn't owe us answers. It doesn't exist to satisfy our curiosity or confirm our theories. It simply exists vast and strange and beautiful. And every now and then, we get to peek through a keyhole and see something extraordinary. Sputnik Planitia is one of those keyholes. A smooth, bright plain of flowing nitrogen ice, erasing craters, renewing itself, existing in a state between solid and liquid, between dead and alive, between the past and the present. A place where geology happens on time scales we can barely comprehend, where ice moves like glaciers, but is made of frozen air, where the surface you see today might sink beneath the depths within a few 100,000 years, replaced by ice that hasn't seen sunlight since before the first modern humans walked the earth. It's easy to overlook the poetry in data, to see measurements, chemical compositions, physical processes, and forget that we're talking about real places, real landscapes, real surfaces that exist right now, billions of miles away, bathed in the faint cold light of a distant sun. But they're there. Sputnik Planitia is there. Not in our imagination, not in a simulation, but actually there on the surface of an actual world, moving slowly, breathing in its own frozen way, continuing its ancient patient cycle beneath skies we'll probably never visit. And just beyond the edges of that smooth plain, where the bright nitrogen ice meets the darker, older terrain, the landscape changes dramatically. Mountains rise, not small hills, not gentle slopes, but towering peaks of water, ice thrust upward by forces we're only beginning to understand. Mountains shouldn't exist on Pluto. Not mountains like these. Not peaks that rise 3-4 kilometers into the thin haze, casting long shadows across frozen plains, standing as tall as the Alps, as enduring as anything carved from granite or basalt. But they do exist, and they're made of something you drink every day: water. When the first high-resolution images of Pluto came back from New Horizons, planetary scientists gathered around their screens, studying the terrain along the western edge of Sputnik Planitia. They expected smoothness, maybe some gentle rolling hills, the kind of subdued topography you might find on an ancient geologically dead world. What they saw instead stopped them cold. Mountains. Sharp, angular, rugged. Some standing alone, others clustered in ranges that stretched for hundreds of kilometers. The highest peaks reached 3,500 meters above the surrounding plains, about the height of the Matterhorn in the Swiss Alps, or Mount Cook in New Zealand. They named them after explorers. Hilary Montes, after Sir Edmund Hillary, the first person to summit Mount Everest. Norgay Montes, after Tenzing Norgay, who stood beside him on that peak in 1953. And Al-Idrisi Montes, named for the 12th century Arab geographer who mapped the known world with extraordinary accuracy. Fitting names for features that redefined what we thought we knew about frozen worlds. Because here's the thing, these mountains aren't made of rock. There is rock on Pluto, deep below the surface, mixed with ice, forming the dense core of the dwarf planet. But the mountains visible from space, the peaks that rise into the sky, the ridges that catch the distant sunlight, they're water ice. Frozen water. The same substance that melts in your glass on a summer afternoon, that forms clouds and falls as rain that carve the Grand Canyon and fills the oceans. But at negative 223 degrees Celsius, water ice doesn't behave like ice on Earth. It behaves like granite. Think about that for a moment. Take the mental image you have of ice-cold, slippery, fragile, something that cracks easily, that melts at the slightest warmth. Now, set that image aside, because on Pluto, water ice is harder than steel. It doesn't crack under pressure. It supports mountains. It doesn't flow. It stands rigid for billions of years. At those temperatures, the molecular structure of ice becomes so stable, so inflexible, that it acts like bedrock. Scientists often describe it this way. On Pluto water, ice is rock. And nitrogen ice, the substance that fills Sputnik Planitia, is more like mud or lava, soft, deformable, capable of flowing over geological time. It's a complete inversion of what we experience on Earth. Here water is soft. It flows. It carves valleys, fills lakes, responds immediately to gravity and temperature. Rock is hard. It resists. It holds its shape for millions of years unless subjected to tremendous forces. On Pluto, the roles are reversed, and that reversal explains why these mountains can't exist at all. Mountains on Earth form through tectonic processes. Plates collide, crust crumples, rock is thrust upward. The Himalayas are still rising today, millimeter by millimeter, as the Indian plate grinds northward into the Eurasian plate. The Andes formed as oceanic crust, subducted beneath South America. The Alps, the Rockies, the Appalachians, all products of plate tectonics of Earth's restless shifting surface driven by heat from the interior. But Pluto doesn't have plate tectonics. It's too small, too cold. Its interior solidified long ago. There are no moving plates, no subduction zones, no continental drift. So, how did these mountains form? The answer lies in a process called isostasy. It's a principle of buoyancy of materials floating or sinking based on their density. Imagine placing a block of wood in water. The wood floats because it's less dense than water. Now, imagine placing a block of iron in that same water. It sinks because iron is denser. The same principle applies to planetary crusts. On Earth, mountains have deep roots extending down into the mantle. The visible peak is only part of the story. Beneath the surface, the mountain's mass displaces denser material, seeking equilibrium. It's like an iceberg. Most of the ice is underwater, supporting the small portion you see above the surface. On Pluto, water ice mountains float on a substrate of denser material, possibly a mixture of nitrogen ice, methane ice, and deeper layers of water, ice compressed by pressure. The mountains aren't being pushed up by tectonic forces. They're floating, rising naturally the way oil rises through water, seeking their level based on density differences. But that raises another question. Why are these mountains here specifically along the edge of Sputnik Planitia and not distributed randomly across Pluto's surface? Scientists believe the mountains might be fragments of Pluto's ancient crust. Before the impact that created Sputnik Planitia basin, this region might have been covered with water ice terrain, similar to the rest of Pluto. Then something big struck. The impact excavated the basin, shattered the crust, created chaos. Over time, nitrogen ice filled the depression, flowing like a viscous liquid. But the fragments of the original water ice crust remained. They floated on, the nitrogen drifted to the edges, accumulated along the boundaries like ice flows pushed to the shore of a frozen lake. It's a landscape shaped by catastrophe and patience. The violence of impact, followed by billions of years of slow adjustment materials sorting themselves by density, finding equilibrium in the deep cold of the outer solar system. And these aren't gentle rounded hills worn smooth by eons of erosion. They're jagged, angular, almost geometric in places, with sharp ridges and steep slopes that suggest youth geologically speaking. If these mountains had been sitting exposed to space for billions of years, micrometeorite bombardment and thermal cycling would have softened their features, rounded their edges, smoothed their peaks. But they look fresh, crisp, as if they formed relatively recently, or as if something has been protecting them from erosion. One possibility is that Pluto's thin atmosphere, despite being incredibly tenuous, provides just enough protection to slow erosion. Another is that the mountains are younger than the surrounding terrain, thrust up more recently, by processes we don't fully understand yet. Or perhaps the nitrogen ice that surrounds them has only recently receded, exposing mountains that had been buried for eons. We don't know for certain, not yet. And that's part of what makes Pluto so fascinating. Every answer leads to 3 new questions. Every discovery reveals how much we still don't understand. Consider the Tenzing Montes Range. It stretches for about 150 kilometers along the southwestern edge of Sputnik Planitia. The peaks rise steeply from the nitrogen ice plain, their slopes reaching angles of 30 to 40 degrees, steep enough that if you were standing at the base looking up, the summit would loom almost directly overhead. But here's something strange. There are no valleys cutting through these mountains, no erosion channels, no signs of material being transported downslope. On Earth, mountains are constantly being worn down by wind water, ice, and gravity. Rivers carve valleys. Glaciers scour U-shaped channels. Rock slides and avalanches redistribute material from high elevations to low. But on Pluto, erosion happens slowly. There's no liquid water to carve channels, no rain to wash sediment downhill. The atmosphere is so thin that wind erosion is negligible, and while temperature changes do occur, Pluto's eccentric orbit brings it closer to the Sun. During part of its 248-year cycle, these changes happen gradually, without the dramatic freeze-thaw cycles that shatter rock on Earth. So the mountains stand, pristine, almost untouched since they formed. There's a lesson in that, if we're willing to listen. We live on a dynamic planet where landscapes change within human lifetimes. Rivers change course. Coastlines erode. Mountains wear down. We're accustomed to impermanence, to the idea that nothing lasts forever, that time inevitably smooths all rough edges. But on Pluto, time moves differently. A mountain that formed 1 billion years ago might look almost the same today. Unchanged, patient, waiting in the cold and the dark, holding its shape against the slow erosion of cosmic radiation and the rare gentle fall of nitrogen snow. It's humbling in a way, to realize that not all places change on human timescales, that there are corners of the universe where a mountain can stand for longer than multicellular life has existed on Earth, and nothing will wear it down. Now, there's been some speculation about whether Pluto might have cryovolcanoes. Volcanoes, but instead of erupting molten rock, they erupt molten ice water mixed with ammonia or methane substances that melt at far lower temperatures than pure water. Some regions on Pluto show features that could be cryovolcanic domes. Wright Mons and Picard Mons are 2 large mountains with central depressions that resemble volcanic calderas. They're enormous, Right Mons is about 150 kilometers across at its base and stands 4 to 5 kilometers high. That's larger than Mauna Loa in Hawaii, one of Earth's biggest volcanoes. But the evidence isn't conclusive. The features could be cryovolcanic, or they could be something else entirely: collapsed impact craters, domed regions where subsurface ice expanded, or even erosional remnants of ancient terrain. New Horizons didn't see any active eruptions. No fresh lava flows, no plumes, no obvious signs that these features formed recently. And honestly, that's okay, because the not knowing is part of the experience. Science isn't about having all the answers immediately. It's about asking better questions, gathering evidence, testing hypotheses, and being willing to say, we don't know yet, but we're working on it. What we do know is this: Pluto's mountains challenge our assumptions about what's possible on small, distant worlds. We assume that without plate tectonics, without volcanic activity, without a thick atmosphere or flowing water, a world would be geologically dead, cratered, unchanging, a museum of impacts, nothing more. But Pluto has mountains. Young-looking mountains made of water ice, harder than granite, floating on seas of frozen nitrogen, standing tall under skies so dark that stars are visible even at midday. And maybe that's the real discovery, not the specific details of mineral composition or formation mechanisms, but the broader revelation the universe is more creative than we give it credit for. It finds ways to build mountains on worlds we'd written off as boring. It finds ways to make ice flow on surfaces cold enough to freeze air. It finds ways to surprise us, to humble us, to remind us that our intuitions, shaped by living on one warm, wet, tectonically active planet, don't always apply elsewhere. Have you ever climbed a mountain? Not necessarily a tall one, even a hill will do. There's something about standing at the base, looking up, feeling the weight of vertical distance, the effort required to ascend. And then, when you reach the top, there's that moment of expansiveness. The world opens up. You see farther than you could from below. Perspective shifts. That's what these mountains offer in a metaphorical sense. A shift in perspective. A reminder that height, mass, endurance, these things exist throughout the universe, not just here. Somewhere right now, on a frozen world, 5 billion kilometers away, mountains stand. Silent. Ancient. Made of ice harder than stone, casting shadows that stretch for hundreds of kilometers across plains of nitrogen snow. And those mountains don't care whether we understand them or not. They simply exist, patient and cold, waiting for the next visitor to arrive, whether that's in a decade, a century, or never. But while these peaks reach upward, something else reaches outward, wrapping Pluto in the faintest embrace. There's air on Pluto. Not much. Not enough to breathe, not enough to feel as wind against your face. But it's there, a whisper of gas clinging to the surface so thin that if you could compress all of Pluto's atmosphere down to sea level pressure on Earth, it would form a layer only about 10 meters thick. 10 meters. That's the height of a 3-story building. Earth's atmosphere compressed the same way would create a layer over 8 kilometers deep. And yet, despite being so incredibly thin, with a surface pressure of only about 10 microbars, roughly 100,000th of Earth's atmospheric pressure, Pluto's atmosphere shouldn't exist at all. Because Pluto is small, its gravity is weak, only about 6% of Earth's surface gravity. If you weigh 150 pounds on Earth, you'd weigh about 9 pounds on Pluto. You could jump 6 times higher. Walk with slow bouncing steps like the Apollo astronauts on the moon, but even more exaggerated. And weak gravity means a world can't hold on to an atmosphere very easily. Gas molecules move fast, especially when warmed by sunlight. If they're moving fast enough to exceed the escape velocity of the world they simply drift away into space, lost forever. On Earth, with our stronger gravity and warmer temperatures, atmospheric escape happens slowly. We lose some hydrogen and helium, the lightest gases, but heavier molecules like nitrogen and oxygen are held firmly in place. Our atmosphere is stable over billions of years, but Pluto's escape velocity is much lower. only about 1.2 kilometers per second compared to Earth's 11.2. That means nitrogen molecules, the primary component of Pluto's atmosphere, are right on the edge. Some have enough thermal energy to escape, others don't. Scientists estimate that Pluto loses somewhere between 10^27 and 10^28 molecules per second to space. That sounds like a lot. And it is about 500 tons of atmosphere every hour continuously bleeding away into the vacuum. Over the 4.5 billion years of Pluto's existence that should have stripped the atmosphere completely. Pluto should be airless like most small bodies in the solar system, like asteroids, like most moons. Just rock and ice under naked starlight with no gaseous envelope to soften the boundary between surface and space. But it has one. And when New Horizons flew past in 2015, studying the atmosphere was one of the mission's highest priorities. The spacecraft watched as Pluto passed in front of a distant star. This technique, called stellar occultation, is extraordinarily sensitive. As the star's light traveled through Pluto's atmosphere, before reaching New Horizons instruments, the atmospheric gases absorbed and scattered specific wavelengths. By analyzing how the starlight dimmed, and at which wavelength scientists could determine the atmosphere's composition, temperature, pressure, and structure, what they found was both expected and surprising. Expected, the atmosphere is mostly nitrogen, about 98%, with traces of methane and carbon monoxide. That matches what spectroscopy had suggested from Earth-based observations. Surprising, the atmosphere extends much farther than predicted. It reaches up to 1,600 kilometers above the surface, roughly the distance from New York to Denver. That's huge proportionally. If Earth's atmosphere extended that far relative to our planet's size, it would reach a quarter of the way to the moon. And even more surprising, the atmosphere has layers, multiple distinct regions of haze stacked like translucent curtains, creating a structure eerily similar to the haze layers on Titan, Saturn's largest moon. When New Horizons captured images of Pluto backlit by the sun, those haze layers appeared as delicate blue arcs surrounding the planet's silhouette. The images are hauntingly beautiful. Pluto, a dark circle against the blackness of space, with these fragile ribbons of blue light wrapping around its edges, catching the sun's rays, glowing softly like the corona during a total solar eclipse. Blue. That's the key detail. The haze appears blue for the same reason Earth's sky is blue scattering. But on Pluto, the particles doing the scattering aren't air molecules, they're tholins. Those complex organic molecules we mentioned earlier, formed when ultraviolet light from the sun breaks apart methane molecules high in the atmosphere. The broken fragments recombine into larger, more complicated structures. Long chains of carbon and hydrogen mixed with nitrogen, creating molecules with dozens or even hundreds of atoms. These tholins are tiny, much smaller than a bacterium, small enough to stay suspended in the thin atmosphere for years, drifting slowly downward, scattering sunlight as they fall. And as they accumulate on the surface, they change color. In the upper atmosphere, fresh tholins scatter blue light, but as they age, as they're exposed to more ultraviolet radiation and cosmic rays, they darken. They turn red, orange, brown. Eventually, they settle onto Pluto's surface, staining the ice, creating the reddish patches and dark equatorial band visible in New Horizons images. It's the same chemistry that gives Titan its orange haze, the same basic process that creates smog in Earth's cities when sunlight reacts with pollution. But on Pluto, it's natural, ancient. A cycle that's been running for billions of years, painting the surface molecule by molecule with the colors of photochemistry. Now, here's where it gets really interesting. Pluto's atmosphere isn't constant. It changes dramatically. Because Pluto's orbit is highly eccentric, stretched into an ellipse, not a circle. At perihelion, its closest approach to the Sun, Pluto comes within about 4.4 billion kilometers of our star. At aphelion, its farthest point, it's nearly 7.4 billion kilometers away. That's a difference of 3 billion kilometers, 50% farther at aphelion than at perihelion. And that difference matters, because Pluto's atmosphere comes from its surface. Nitrogen ice warmed by sunlight sublimates transitions directly from solid to gas without melting. The vapor rises, creating atmospheric pressure. More sunlight means more sublimation, which means a thicker atmosphere. But as Pluto moves away from the sun, the surface cools. Sublimation slows. The nitrogen in the atmosphere starts to freeze, falling back to the surface as snow. The atmospheric pressure drops. Over the course of Pluto's 248-year orbit, the atmosphere might collapse almost entirely, condensing back onto the surface, leaving Pluto nearly airless during the coldest decades of its long year. When New Horizons arrived in 2015, Pluto was relatively close to perihelion. It had passed its closest point to the Sun in 1989 and was still warm by Pluto's standards. The atmosphere was relatively thick and extended. But in a few more decades, as Pluto continues moving outward, that atmosphere might shrink dramatically. Some scientists wondered if we'd even find an atmosphere in 2015. Previous observations from Earth watching stars blink out as Pluto passed in front of them showed increasing atmospheric pressure through the 1980s and 1990s, but models predicted it might start collapsing soon. If New Horizons had arrived a few decades later, it might have found a very different world. We got lucky with the timing, caught Pluto during a moment when it was breathing out, when its surface was warm enough to sustain that tenuous envelope of gas. But why does the atmosphere exist at all? If Pluto loses hundreds of tons every hour and has been doing so for billions of years, where does the nitrogen come from? The answer lies in Sputnik Planitia, that massive reservoir of nitrogen ice constantly renewing itself through convection is the source. As long as Sputnik Planitia exists, as long as there's nitrogen ice on the surface being warmed by sunlight, Pluto will have an atmosphere. It's a balance. Nitrogen sublimates from the surface, creating atmospheric pressure. Nitrogen escapes to space. More nitrogen sublimates to replace it. The cycle continues. But it's a precarious balance. If something disrupted Sputnik Planitia, if a massive impact excavated most of the nitrogen ice, or if Pluto's orbit shifted dramatically, the atmosphere could vanish. Not slowly over millions of years, but within decades or centuries, rapid by geological standards. There's something profound about that fragility. We think of atmospheres as permanent features. Earth has had an atmosphere for over 4 billion years. Venus, Mars, the gas giants, they have all maintained their atmospheres across geological time. But Pluto's atmosphere is ephemeral, seasonal, dependent on the delicate interplay of orbital mechanic surface composition and solar heating. It's a reminder that not all planetary features are stable, that some things exist only under specific conditions, and when those conditions change, they vanish, like a desert lake that fills during the rainy season and dries to dust in summer. Temporary but no less real for its impermanence. And there's another layer to this mystery. Pluto's atmosphere isn't just escaping into space randomly. It's structured, organized. The stellar occultation data showed evidence of atmospheric waves, large-scale oscillations, similar to gravity waves in Earth's atmosphere. These waves suggest that Pluto's atmosphere is dynamic, not static. Something is stirring it, creating patterns driving circulation. But what Pluto doesn't have weather in the way Earth does. No hurricanes, no thunderstorms, no fronts bringing rain or snow. The sun is too distant, too dim to drive energetic atmospheric convection. And yet, something is moving the air. One possibility is topography. Mountains like the ones we discussed earlier could create standing waves as thin winds flow over them. Or temperature differences between Sputnik Planitia's bright ice and the darker surrounding terrain might drive weak circulation patterns. Or tidal forces from Charon, Pluto's largest moon, might be squeezing and relaxing the atmosphere, creating subtle pressure variations that propagate as waves. We don't know yet. The data from New Horizons is incredible, but it's a snapshot. a single day in Pluto's long year. To understand atmospheric dynamics, we'd need continuous observations over months or years. We'd need to watch how pressure changes, how haze layers shift, how the atmosphere responds to seasonal variations in sunlight. Maybe someday we'll go back. Maybe future missions will place instruments on Pluto's surface measuring atmospheric conditions, in real time tracking the slow collapse as Pluto moves toward aphelion. Or maybe we'll never know for certain, and Pluto's atmosphere will remain partially mysterious, understood in broad strokes, but full of small, unresolved questions. Have you ever stood outside just before sunrise when the sky begins to brighten, but the sun hasn't yet appeared? There's this quality to the light, soft, indirect, neither day nor night. The atmosphere glows, scattering sunlight that hasn't reached the ground yet. It's liminal, in between. That's what Pluto's atmosphere feels like metaphorically. Not a full, robust atmosphere like Earth's, but not an airless surface either. Something in between. A delicate shell of gas, glowing faintly, separating surface from space with the thinnest possible boundary. And within that boundary, chemistry happens. Sunlight breaks molecules apart. Fragments recombine. Tholins form, drift, fall. The atmosphere becomes a laboratory, a place where organic chemistry unfolds, slowly, patiently creating complexity from simple ingredients. Some scientists speculate about whether Pluto's atmosphere and the organic molecules it produces might have any connection to the origins of life. Not on Pluto itself, it's far too cold, far too isolated. But perhaps on other worlds, perhaps in the early solar system when planets were still forming, when ice-rich bodies like Pluto were more common in the inner regions. Could tholins have seeded Earth with organic molecules? Could atmospheric chemistry on distant frozen worlds have contributed to the prebiotic soup that eventually gave rise to life? It's speculative. There's no direct evidence. But it's a reminder that even the most remote hostile places in the solar system are connected to us in ways we're only beginning to understand. Chemistry is universal. The same reactions that create tholins in Pluto's atmosphere happened in Earth's early atmosphere. The same physics that drives atmospheric escape on Pluto once drove atmospheric escape on Mars, stripping away much of that planet's early atmosphere and transforming it from a potentially habitable world into the cold desert we see today. We are not separate from these distant places. We are made of the same elements, governed by the same laws, part of the same cosmic story. Pluto's thin blue atmosphere is not an alien thing. It's a variation on a theme, a different verse in a song we're all singing, whether we realize it or not. And beyond that fragile atmosphere orbiting in the darkness, 5 companions keep watch. Pluto is not alone. The 5 moons circle it in the darkness. 5 companions, each following its own path, each with its own story. And together, they create something most planetary systems don't have: chaos. Not the everyday kind of chaos, messy, unpredictable, random, but mathematical chaos. The kind physicists describe with equations where tiny changes in initial conditions cascade into dramatically different outcomes, where orbits don't settle into neat, predictable patterns, but tumble and wobble in ways that can't be fully predicted even with supercomputers. It's beautiful in its own strange way. The dance of bodies bound by gravity, yet refusing to fall into simple rhythms. The largest moon, Charon, was discovered in 1978. Astronomer James Christie was examining photographic plates of Pluto, taken at the United States Naval Observatory in Flagstaff, Arizona. The images were slightly blurry, common for ground-based astronomy, but Christie noticed something odd. Pluto looked elongated, bulged on one side. Not in every image, but periodically, as if something was there, and then not there, appearing and disappearing in a regular pattern. He realized what he was seeing: a moon. So close to Pluto, and large enough relative to the planet, that in telescopes from Earth, the two often blurred together into a single elongated smudge. Charon is enormous for a moon, about half the diameter of Pluto itself. If Earth had a moon that proportionally large, it would be nearly 6,400 kilometers across, about the size of Mars. Our moon, in comparison, is only about a quarter of Earth's diameter. Because Charon is so large relative to Pluto, the two don't orbit like a typical planet-moon system. Instead, they orbit each other. The center of their mutual orbit, the barycenter, isn't inside Pluto. It's in the space between them, about 2,000 kilometers from Pluto's surface. This makes them a binary system. Two bodies locked in an eternal dance, circling a point in empty space. And they're tidally locked. Not just Charon showing the same face to Pluto as our moon does to Earth. Both are locked. Pluto always shows the same face to Charon. Charon always shows the same face to Pluto. They orbit each other every 6.4 days, and they rotate on their axes every 6.4 days, perfectly synchronized. If you stood on the side of Pluto facing Charon, you would see that moon hanging motionless in the sky, never rising, never setting, frozen at the same position forever. And if you stood on the opposite hemisphere, you would never see Charon at all, ever. It would be permanently hidden below the horizon, as unreachable as the far side of the moon was to people on Earth before we sent spacecraft there. Tidal locking happens because of friction. Gravitational forces create tides bulges in a world shape, stretched toward and away from the body it's orbiting. As the world rotates, those tidal bulges move, and the friction of that movement dissipates energy, gradually slowing the rotation. Over millions or billions of years, the rotation rate synchronizes with the orbital period. Earth and the moon are headed toward mutual tidal locking. Right now, only the moon is locked to Earth, but Earth's rotation is slowing by about 1.7 milliseconds per century because of tidal friction. Eventually, in billions of years, Earth will show the same face to the moon always. The moon will hang motionless in the sky, above one hemisphere, invisible to the other. Days will lengthen until one Earth day equals one lunar month. But that's far in the future. For Earth and Moon, the locking is incomplete. For Pluto and Charon, it's already done. They reached that final configuration long ago, settling into a stable equilibrium where both worlds are locked, facing each other across the void, eternal partners in an endless waltz. And then there are the other four moons. Nix and Hydra were discovered in 2005 using the Hubble Space Telescope. Kerberos and Styx followed in 2011 and 2012. All four are small, irregularly shaped chunks of ice and rock, ranging from about 10 to 50 kilometers across. Compared to Charon's 200-kilometer diameter, they're tiny, barely visible in even the best telescopes. But their orbits revealed something unexpected. They're not chaotic in their paths. The orbits are stable, predictable, nearly circular. But their rotations are chaotic, wildly, unpredictably chaotic. Hydra, for example, doesn't spin like a top with a steady axis. It tumbles. Its rotation axis wobbles, precesses, changes orientation in ways that can't be precisely predicted more than a few decades into the future. Sometimes it spins quickly, sometimes slowly. Sometimes the axis points one direction, sometimes another. Scientists describe the rotation period as ranging from 24 to 89 hours. That's not uncertainty in measurement, that's actual variation. The moon doesn't have a fixed day length, it changes. Why? Because Hydra, like the other small moons, orbits in the gravitational field of not one body but two. Pluto and Charon both pull on it. And because Charon is so massive relative to Pluto, the combined gravitational field isn't smooth, it's lumpy, uneven. As Hydra orbits, it feels a constantly changing gravitational tug, sometimes stronger from Pluto, sometimes from Charon, sometimes from both, at angles that create torque. That torque makes the moon tumble. It's like trying to balance a pencil on your finger. If the pencil is perfectly vertical and perfectly still, it will balance. But the slightest wobble, the tiniest vibration, and it tips, falls. The system is unstable. And Hydra's rotation is like that, balanced on a knife edge where tiny gravitational variations accumulate into large-scale tumbling. The same thing happens with Nix Kerberos and Styx. All 4 small moons tumble chaotically, their rotation periods varying, their axes wandering. If you were standing on the surface of Hydra, you wouldn't experience a regular day-night cycle. Sometimes the sun, that distant dim point of light, would rise and set every 24 hours, sometimes every 89 hours. Sometimes it would spiral around the sky in strange loops, never quite setting, or never quite rising, depending on how the moon happened to be oriented that month. It's disorienting just to imagine. Our experience of time is so tied to regular cycles, day and night, seasons, the moon's phases. We build our lives around predictable celestial rhythms. But on Hydra, there is no rhythm, only chaos. And yet, despite the chaos, the system is stable. The moons aren't going to crash into each other. They're not going to be ejected into space. Their orbits are locked into a pattern called orbital resonance. Hydra orbits Pluto every 38.2 days, Nix every 24.9 days, Styx every 20.2 days, Kerberos every 32.2 days. Those numbers aren't random, they're related by simple ratios. Hydra completes 2 orbits in almost exactly the time Styx completes 3. Nix completes 3 orbits in nearly the time Hydra completes 2. The moons pass each other at regular intervals, their gravitational interactions timing out to create a stable configuration. It's like a cosmic clockwork, but instead of rigid gears, there are orbits. And the gears don't mesh perfectly, they wobble, they slip, they create friction. But they keep turning, kept in place by the balance of forces. Scientists believe all 5 moons form from the same event, a collision. Billions of years ago, something big struck Pluto. Not the impact that created Sputnik Planitia that was more recent. This was earlier. The collision threw debris into orbit around Pluto. That debris coalesced gravity, pulling it together into larger clumps. The biggest clump became Charon. The smaller pieces became the 4 outer moons. This is the same process that formed Earth's moon. About 4.5 billion years ago, a Mars-sized object struck the young Earth. The impact vaporized rock threw molten material into orbit, and from that orbiting debris, the moon formed. Evidence for this comes from the moon's composition. It matches Earth's mantle, not Earth as a whole. As if the moon is made of material that was once part of Earth's outer layers, blasted into space and reassembled in orbit. Pluto's moons likely have a similar origin story. Collision, debris, accretion, family born from violence. But here's a question that might seem simple but isn't. What makes something a moon? Size doesn't define it. Some moons are larger than planets. Proximity doesn't define it. Some moons orbit far from their parent worlds. Composition doesn't define it, nor does shape, temperature, or surface features. The only definition that matters is gravitational. A moon is a body that orbits a larger body, which in turn orbits a star. That's it. Everything else is secondary, but language shapes how we think. When we call Charon a moon, we imply a hierarchy. Pluto is the planet or dwarf planet, and Charon is the subordinate companion, the smaller partner, the one that exists in relation to something larger. But as we've seen, that's not quite right. Pluto and Charon orbit each other. Neither is dominant, they're partners. Equals almost. And some scientists argue we should call them a double planet. 2 worlds bound together, circling a point between them. The International Astronomical Union hasn't officially adopted that terminology, but it's a reminder that our categories are imperfect. Reality doesn't care about our labels. It simply exists, and we do our best to describe it with words that were invented for different contexts, different scales, different experiences. Have you ever felt the pull of something larger than yourself? A person, a place, a calling? That sense of orbiting around something drawn by a force you can't fully explain. In a way, we're all in orbit around something. Family, work, passions, responsibilities. We circle, we're pulled, we maintain balance by moving forward while being tugged inward. Pluto and Charon are like that. Not metaphorically, literally. Two bodies held in balance by gravity and motion. If they stop moving, they would fall together, collide, merge. But they don't stop. They keep dancing, and the dance keeps them apart. And around them, the four smaller moons tumble in the darkness, chaotic and free, yet bound by the same forces that hold everything else together. There's a beauty in that chaos, a reminder that order and disorder can coexist, that predictability and randomness are not opposites but partners. The orbits are stable, the rotations are chaotic. Both are true, both are necessary. When New Horizons flew past, it captured images of all 5 moons. Not just Charon, which filled the frame with detail, showing craters, canyons, and strange dark regions, but the 4 small moons as well. They appeared as points of light, sometimes elongated enough to hint at their irregular shapes, but mostly just there, present. Witnesses to the flyby, reflecting sunlight back toward the spacecraft, marking their positions in the cosmic dance. The spacecraft couldn't linger. It was moving too fast. But in the hours around closest approach, it turned its cameras toward each moon, in turn gathering data, measuring brightness, tracking positions, adding to our understanding of this strange distant system. And what we learned is, this even at the edge of the solar system, even in the cold and the dark, even on small forgotten worlds that will never be visited by humans, there is complexity, there is structure, there is beauty. The universe doesn't simplify as you move outward. It doesn't become empty, boring, predictable. It becomes different, stranger, full of phenomena that don't happen anywhere else, governed by conditions that exist nowhere else, creating landscapes and dynamics that challenge everything we thought we understood. Pluto's moons are a reminder of that strangeness, a system where the largest moon is so big it creates a binary planet, where the smaller moons tumble chaotically, their days unpredictable, their rotations governed by the competing pulls of 2 massive bodies, where orbital resonances create stability within chaos, where violence long ago created a family that still orbits together, bound by gravity, separated by space, dancing in the dark. And the largest of those companions, Charon, holds mysteries of its own. Charon is broken, not shattered, not destroyed, but cracked, scarred by enormous fractures that run for hundreds of kilometers across its surface, cutting through ancient ice, diving down into depths that could swallow mountains. Some of these canyons reach 9 kilometers deep. That's deeper than the Grand Canyon, deeper than the Mariana Trench. If you stood at the rim and looked down the bottom, would be lost in shadow too far below to see clearly even in the bright, reflected light of Pluto hanging in the sky above. Something tore Charon apart, and the evidence of that violence is written across its surface in scars that have lasted billions of years. When New Horizons captured the first detailed images of Charon, scientists expected to see a cratered ancient surface, something similar to our moon's highlands perhaps. Saturated with impacts geologically dead, a museum of the early solar system's chaotic violence. What they saw instead was far stranger. Yes, there were craters, many of them, but there were also vast smooth plains in the southern hemisphere, and across the equatorial and northern regions, a network of canyons, cliffs, and fractures so extensive that it looked as if the entire moon had been stressed nearly to the breaking point. The largest canyon system is called Serenity Chasma. It stretches over 1,800 kilometers longer than the distance from Los Angeles to Denver. In some places, the canyon walls rise 7 to 9 kilometers above the floor. That's about the height of Mount Everest measured from sea level. Imagine standing at the base of Everest and looking up at the summit. Then imagine that instead of a mountain, you're looking at a cliff wall, vertical or nearly so. A wall of water ice frozen harder than steel rising into the black sky. And Serenity Chasma isn't alone. There are others. Argo, Chasma, Manjet, Chasma, Kalushe, Chasma. Together, they form a network that suggests Charon's entire surface was under tremendous stress, stretching, cracking, pulling apart. But why? What could cause an entire moon to fracture? The answer lies in water. Or rather, in what happens when water freezes. Most substances contract when they freeze. Liquid cools, molecules slow down, they pack more tightly together. The solid form is denser than the liquid form. This is normal. Expected. If you put a bottle of olive oil in the freezer, it will shrink slightly as it solidifies. But water is strange. Water expands when it freezes. Ice is less dense than liquid water. That's why ice floats, why frozen pipes burst, why glaciers can crack solid rock. When water turns to ice, it takes up about 9% more volume. Now, imagine Charon billions of years ago. Not the cold frozen world we see today, but a young moon still warm from its formation. Deep beneath its surface, there might have been liquid water. Not a vast ocean like Europa or Enceladus, but pockets of liquid kept warm by residual heat from the moon's formation, by the decay of radioactive elements, by tidal flexing, as Charon and Pluto settled into their current locked configuration. Over time, that heat radiated away into space. The interior cooled, and the liquid water began to freeze. As it froze, it expanded. And as it expanded, the surface had to accommodate that expansion. The outer shell of Charon's solid ice, already frozen, was pushed outward, stretched, stressed, and eventually it cracked. This process is called cryotectonics. Not plate tectonics, where heat from the interior drives convection and moves crustal plates, but tectonics driven by cold. By the expansion of freezing water, by the contraction of cooling material, by the slow, patient transformation of a warm, dynamic world into a cold, static one. It's the opposite of what happens on Earth. Here, our planet's interior is hot. Molten rock convects, drives plate motion, creates mountains and ocean basins. The process is driven by heat escaping from the interior. On Charon, the process was driven by cold entering the interior, and the result is written across the surface in those vast canyons. Evidence of a world that expanded, cracked, and froze into its current form. But there's another mystery on Charon, something that puzzled scientists from the moment they saw the first clear images. The North Polar region is dark. Not just shadowed, but genuinely dark, stained, as if someone had taken a giant brush dipped in reddish-brown paint and swept it across hundreds of thousands of square kilometers of ice. They call it Mordor Macula, named fittingly after the dark land in Tolkien's The Lord of the Rings. A region of shadow where light seems dimmer, colors seem muted, and something about the surface is fundamentally different from the brighter ice around it. At first, scientists weren't sure what caused Mordor Macula. The dark material could be intrinsic. Something erupted from Charon's interior, perhaps mixed with organic molecules or minerals that naturally appear dark. Or it could be extrinsic material falling onto the surface from space deposited over billions of years. The answer, research suggests, is extrinsic, but not in the way you might think. The dark material is likely tholins, those same complex organic molecules formed in Pluto's atmosphere when sunlight breaks apart methane. The tholins drift down, settle on Pluto's surface, staining parts of it red and orange. But some of that atmosphere escapes. Remember, Pluto loses hundreds of tons of atmosphere every hour. Most of it drifts away into space, lost forever. But some of it doesn't drift far. Some of it encounters Charon. Charon orbits Pluto at a distance of about 19,600 kilometers, roughly the distance you'd travel if you drove around Earth's equator halfway. Close enough that Pluto's escaping atmosphere can reach it. And when those gas molecules encounter Charon's surface frigid at negative 220 degrees Celsius, they freeze instantly, stick to the ice, accumulate over millions of years, and the tholins accumulate with them, settling like dust. building up slowly grain by microscopic grain, painting the ice a darker shade. But why only at the North Pole? Why not uniformly across the entire surface because of Charon's orientation? Remember, Charon is tidally locked to Pluto. One face always looks toward Pluto, the other face always looks away. And because of the geometry of the system, the North Polar region is positioned in a way that maximizes its exposure to Pluto's escaping atmosphere. It's like standing at the edge of a campfire. If you face the fire, your front gets warm, your back stays cold. Charon's North Pole faces into the stream of escaping gas. It catches more tholins, accumulates more dark material, while the rest of Charon remains relatively pristine, covered in bright, clean water ice. Over billions of years, that differential accumulation creates Mordor macula, a natural process, slow and patient painting one region dark while leaving others bright. And there's something poetic about that. The idea that Chiron is being painted by Pluto's breath, that the gas escaping from one world is leaving a mark on another, a connection between two bodies, visible physical, written in color and chemistry. Scientists have found similar dark regions on other moons. Iapetus, one of Saturn's moons, has a dark hemisphere and a bright hemisphere. The dark side is covered with material that might have originated from Phoebe, another of Saturn's moons, whose orbit carries it through a region where dust and particles are more common. That dust spirals inward, encounters Iapetus, and settles preferentially on one side, creating a two-tone world. It's a reminder that moons don't exist in isolation. They're part of systems. They influence each other. Material moves between them. Chemistry connects them. What happens on one world can leave traces on another. Now, let's talk about those smooth plains in Charon's southern hemisphere. They're called Vulcan Planum, flat, relatively crater-free, much younger than the surrounding terrain. And they suggest something remarkable. Charon might have had cryovolcanism. Not volcanoes erupting molten rock, but volcanoes erupting molten ice. Water mixed with ammonia, perhaps, or methane substances that melt at much lower temperatures than pure water. Erupting from fractures in Charon's crust, flowing across the surface like lava, filling in old craters, smoothing the terrain. The evidence isn't definitive. New Horizons didn't see any active eruptions, but the geology is suggestive. Smooth plains, relatively few craters, a surface that looks resurfaced, renewed within the last billion years or so. If Charon had cryovolcanism, it means the moon wasn't entirely cold inside. Something was generating heat, perhaps radioactive decay, perhaps tidal flexing during the era when Charon and Pluto were still settling into tidal, lock their orbits slightly eccentric, creating enough stress and friction to melt ice deep inside. And once melted, that ice had to go somewhere. Pressure would build, fractures would open, and the liquid would erupt, flowing across the surface, freezing into new plains. It's the same basic process as volcanism on Earth or Io, just colder, slower, driven by different chemistry, but fundamentally similar heat from the interior, forcing material to the surface, reshaping the landscape, erasing the past. Have you ever tried to fix something that's broken, patched a crack, glued pieces back together, smoothed over damage? Charon is like that. A world that broke, that cracked under stress, and then perhaps healed itself, filling in some of those cracks with fresh ice, creating new surfaces over old wounds. But the healing was incomplete. The canyons remain. The fractures are still visible. Billions of years later, the scars persist, testament to a moment of transformation when Charon changed from what it was into what it is. There's a misconception about moons. We tend to think of them as simple, smaller than planets, less interesting. Rocks orbiting rocks with little geology, little history, little worth studying beyond their role in stabilizing their parent planet's rotation or creating tides. But Charon proves that's wrong. Moons can be complex. They can have histories as rich as planets. They can crack, freeze, erupt, resurface, accumulate material from neighboring worlds, and change dramatically over time. Charon is half the size of Pluto, but in some ways, it's just as interesting, just as full of mysteries, just as deserving of attention and study. When New Horizons flew past, it spent almost as much time studying Charon as it did studying Pluto. The spacecraft turned its cameras, spectrometers, and other instruments toward the large moon, drinking in data, measuring surface composition, mapping topography, tracking how light reflected from different regions. And what that data revealed is a world with depth, with layers, with a history written in ice and shadow and canyons and plains and dark stains and bright craters. A world that was once warm enough to have liquid water beneath its surface. That froze, expanded, cracked. That might have erupted molten ice filling in some of its own scars. That now sits locked in position, facing Pluto, eternally accumulating tholins on its north pole, slowly being painted by the breath of another world. Charon is a reminder that even companions have stories, that even secondary bodies, moons, satellites, objects defined by their relationship to something larger are worth studying for their own sake. And in studying them, we learn something fundamental. The universe doesn't waste complexity. Even in the cold, even at the edge, even on small worlds that will never host life or be visited by humans, there is geology. There is change. There is history unfolding, slowly, patiently written in ice that remembers everything and reveals it only to those who look carefully enough. But why does all this ice on Pluto, on Charon, across this entire system, wear such strange and vivid colors? Color is memory. On Earth, rust tells the story of iron meeting oxygen and time. Tree rings record years of rain and drought. The patina on old copper speaks of decades exposed to weather. Color isn't just aesthetic, it's information, evidence, a record of chemistry unfolding slowly across years, centuries, millennia. And on Pluto, color tells a story 5 billion kilometers long, the story of sunlight reaching across the void, of molecules breaking apart and reforming, of organic chemistry happening so slowly that a single reaction might take centuries to complete, of ice that remembers every photon that ever touched it. Pluto is red, not uniformly, not everywhere, but in patches, in streaks, in broad equatorial bands that wrap around the planet like a rust-colored belt. And understanding why, understanding the chemistry that creates those colors, reveals something profound about how the universe builds complexity from simplicity, even in the coldest, most remote places imaginable. When scientists first processed the color images from New Horizons, they were struck by the range. Pluto isn't monochrome. It's not just white ice and black shadows. It's red-orange in some regions, tan in others, bright white across Sputnik Planitia, with subtle pink and yellow tones in certain areas. The color variation is complex, nuanced, beautiful in a way that no one predicted. And almost all of that color comes from one class of molecules, tholins. We have mentioned tholins before. They form in Pluto's upper atmosphere when ultraviolet light from the sun breaks apart methane molecules. The fragments carbon, hydrogen, nitrogen radicals collide with each other with nitrogen molecules with other methane fragments. They stick together, bond, form larger structures. One methane molecule has 1 carbon atom and 4 hydrogen atoms. Simple, small, a gas at Earth temperatures but frozen solid on Pluto's surface. But when that methane is broken apart by UV light and the pieces recombine, they don't necessarily reform methane. They can create ethane 2 carbons, 6 hydrogens, or propane 3 carbons, 8 hydrogens, or longer chains, rings, branch structures, some containing nitrogen, some containing oxygen if any is present. These larger molecules are called tholins. The name comes from the Greek word tholos, meaning muddy or hazy. Carl Sagan and his colleague Bishun Kare coined the term in the 1970s while studying similar chemistry in Titan's atmosphere. They needed a word for the complex reddish-brown organic gunk that formed in their lab experiments simulating Titan's atmosphere. Tholins fit. And tholins are everywhere in the outer solar system. They give Titan its orange haze. They stain the surface of Triton Neptune's largest moon. They color parts of Centaur's and Kuiper Belt objects. And they paint Pluto red. But here's what makes tholins fascinating. They're not a single compound. They're a mixture. A family of molecules ranging from small, maybe a dozen atoms, to large hundreds or thousands of atoms linked together in complex arrangements. Some are linear chains, some are branched, some form rings. Some are aromatic with electrons shared across multiple atoms in stable configurations. Analyzing tholins is like analyzing soil. You can't point to a single molecule and say, that's a tholin. Instead, you describe the mixture, the distribution of molecular weights, the ratios of carbon to hydrogen to nitrogen, the functional groups present, the overall chemical signature. And that signature tells a story about the environment where the tholins formed. Temperature, pressure, the intensity of UV radiation, the availability of different starting materials. All of these influence which molecules form, how large they grow, and what color they become. On Pluto, the tholins start as fresh light-colored particles in the upper atmosphere. As they drift down through the haze layers, they're exposed to more radiation. They age, darken. By the time they reach the surface, they have turned red-orange. And once on the surface, they continue to change. Cosmic rays, high-energy particles from distant supernovae, and the sun strike them, break bonds, create new radicals that react and form even more complex structures. Over millions of years, this process creates a gradient. The youngest surface tholins are lighter. Older deposits are darker, redder. The oldest might be almost black, like coal having undergone so many chemical transformations that their original structure is unrecognizable. And because tholins are organic molecules containing carbon, hydrogen, nitrogen, they've sparked discussions about whether they might be relevant to the origins of life. Not on Pluto. It's far too cold. There's no liquid water, no energy source to drive the kind of chemistry life requires. But in the early solar system, when ice-rich bodies like Pluto were more common in the inner regions, before the giant planets migrated to their current positions, tholins might have been delivered to Earth via comets and asteroids. And once here in a warmer, wetter environment, those tholins could have been broken down, dissolved, their component molecules made available for further reactions. Some scientists speculate that tholins might have contributed to the prebiotic soup from which life eventually emerged. It's speculative. There's no direct evidence, but it's a reminder that organic chemistry is universal. The same processes that create tholins on Pluto created similar molecules in Earth's early atmosphere. The same physics that drives photochemistry 5 billion kilometers from the sun once drove photochemistry here. We're not separate from these distant worlds. We're connected by chemistry, by history, by the fact that we're all made of the same elements forged in the same stars, following the same laws. Now, Pluto's red regions aren't distributed randomly. The most intense coloration is around the equator, in a broad band that circles the planet. Scientists call it the red belt. It's particularly prominent on the side of Pluto that faces away from Charon, the anti-Charon hemisphere. Why there? Why not uniformly across the entire surface? One possibility is atmospheric circulation. Pluto's thin atmosphere, despite being incredibly tenuous, does move. Temperature differences between Sputnik Planitia's bright ice and the darker surrounding terrain might drive weak winds. Those winds could transport tholins, concentrating them in certain regions, creating the observed pattern. Another possibility is surface chemistry. Different types of ice, nitrogen, methane, water have different reflectivities, different temperatures, different abilities to hold onto tholins. Maybe the equatorial region has surface conditions that favor tholin accumulation. Or maybe it's older, having been exposed longer, giving tholins more time to build up and darken. Or maybe it's related to Pluto's orbital cycle. Remember, Pluto's orbit is eccentric. Its distance from the Sun varies dramatically. During some parts of the orbit, the equator receives more sunlight. During others, the poles do. Over millions of years, this variation might create zones where tholins are more or less stable, more or less likely to sublime away or be buried by fresh ice. We don't know for certain. The data from New Horizons is rich, but it's a snapshot. One day in Pluto's 248-year orbit, one season in a cycle that takes longer than the entire history of the United States. To truly understand how colors change, we'd need to observe Pluto over decades, tracking how sublimation deposition and atmospheric chemistry respond to changing solar illumination. But even without those long-term observations, we can learn from comparison. Pluto's colors are similar to those on Triton, Neptune's largest moon. Triton is about the same size as Pluto, has a similar surface composition, nitrogen ice, methane, ice, water ice, and shows similar reddish coloration in certain regions. Scientists believe Triton was once a Kuiper Belt object like Pluto. It formed in the same region from the same materials. But at some point billions of years ago, it wandered too close to Neptune. The giant planet's gravity captured it, pulled it into orbit, and in the process, Triton's original orbit was twisted, warped, circularized through tidal interactions that generated tremendous heat, possibly melting the interior, resurfacing the moon, erasing most evidence of its early history. But the chemistry remains. The tholins remain. Evidence of a shared origin, a common birthplace in the cold outer reaches of the solar system. And there's another world with tholins worth mentioning, Titan. Saturn's largest moon, the only moon in the solar system with a thick atmosphere. Titan's atmosphere is nitrogen like Earth's, but with a few percent methane. And that methane, broken apart by sunlight and energetic particles from Saturn's magnetosphere, creates tholins. Lots of them, so many that they form a thick orange haze completely obscuring the surface from visible light. Titan's surface is hidden. When the Cassini spacecraft orbited Saturn from 2004 to 2017, its cameras couldn't see Titan's ground through the haze. Instead, mission scientists used radar and infrared instruments to peer through the atmosphere, revealing lakes of liquid methane, river channels, sand dunes, and a complex landscape shaped by processes both familiar and alien. But that orange haze, tholins, raining down onto the surface, accumulating over millions of years, creating an organic, rich environment that some scientists think might support unusual forms of chemistry, maybe even life based on liquid methane instead of liquid water. It's the same chemical family as on Pluto, but produced in a different environment with different outcomes, creating a different world. Have you ever thought about how the same ingredients can create vastly different results depending on context? Flour, water, yeast, combine them one way. You get bread. Another way, pasta. Another way, cake. The ingredients matter, but so do temperature time technique. Tholins are like that. Carbon, hydrogen, nitrogen, simple building blocks. But depending on temperature, pressure, radiation, and time, they create different structures, different colors, different worlds. On Pluto, they paint ice red. On Titan, they create an orange haze. On Triton, they stain dark regions near the poles. Same chemistry, different contexts, different stories. And here's something subtle that often gets missed: color is diagnostic. When scientists study spectroscopy data from Pluto, analyzing which wavelengths of light are absorbed and reflected by the surface, they can identify specific molecules. Methane ice absorbs strongly in certain near-infrared wavelengths. Nitrogen ice has its own signature. Water ice has another. But tholins, they absorb across a broad range. They don't have sharp, distinctive features like simpler molecules. Instead, they create a gradual slope in the spectrum, a reddening, a general darkening at shorter wavelengths. That's their signature. Not precision, but breadth. Not a single note, but a chord. And by analyzing that chord, scientists can estimate the age of the surface. Fresher ice with fewer tholins looks brighter. Older ice, exposed, longer, looks darker and redder. It's like tree rings, but written in color. So, when we look at Pluto and see red regions, we're seeing time. We're seeing the accumulation of billions of years of photochemistry. Every photon that struck a methane molecule, every radical that formed every bond that broke and reformed all of it, recorded in the color of the ice. It's slow, glacially slow, a process that takes centuries to produce visible change, but it's relentless, patient. As long as there's sunlight, as long as there's methane, as long as Pluto orbits the sun, the chemistry continues. Tholins form, they fall, they accumulate, they darken. And the planet changes color one molecule at a time. There's something humbling about that, about processes so slow that human lifetimes are irrelevant, about change that happens regardless of observation, regardless of attention, regardless of whether anyone is watching or recording or understanding. Pluto was turning red long before humans existed. It will continue turning red long after we're gone. The chemistry doesn't care about us. It simply unfolds following the laws of physics and chemistry, creating complexity. Because that's what the universe does when energy and matter interact over time. And maybe that's the real lesson of tholins. Not the specific molecules, not the exact mechanisms, but the broader truth. Complexity emerges. Naturally, inevitably. Given energy, given time, given simple ingredients, the universe builds. It creates. It transforms. From methane to tholins. From simple to complex. From transparent to red. From young to old. And all of it visible if you know how to look written in color across the face of a frozen world, 5 billion kilometers from home. But Pluto isn't unique in this chemistry. It's part of a neighborhood, a region of space filled with similar worlds. Pluto has neighbors, thousands of them, tens of thousands, maybe hundreds of thousands depending on how small you're willing to count, scattered across a vast region beyond Neptune's orbit. These frozen worlds drift in the darkness remnants of the solar system's formation, untouched archives of the ancient past. This is the Kuiper Belt, Pluto's true home. And understanding this neighborhood changes everything we thought we knew about the edge of the solar system, and why Pluto's demotion wasn't a dismissal, but a revelation. For most of human history, we believed the solar system ended at Neptune. Discovered in 1846 through mathematical prediction rather than direct observation, Neptune was the outermost known planet. Beyond it, nothing. Empty space, the void between our sun and the nearest stars. But that belief was wrong, and the first hint came in 1930 with Pluto's discovery. For decades, Pluto was an outlier, an odd little world smaller than expected, with a strange tilted orbit that sometimes brought it inside Neptune's path. It didn't quite fit. Too small to be a gas giant, too far to be rocky like the inner planets, eccentric, unusual, an anomaly. But in 1992, everything changed. Astronomers David Jewett and Jane Liu, working at the Mauna Kea Observatory in Hawaii, discovered something beyond Neptune, not Pluto, something else. A small icy body about 250 kilometers across, orbiting the sun at a distance of about 44 astronomical units, 44 times Earth's distance from the sun. They named it 1992 QB1, not a poetic name, just a designation. But its discovery was monumental, because if there was one object beyond Neptune, there were probably more, many more. And over the following years, as telescopes improved and surveys deepened, more objects appeared. Dozens, then hundreds, then thousands. The Kuiper Belt revealed itself. A vast disc-shaped region extending from about 30 to 50 astronomical units from the sun. populated by icy bodies, most small, some large, all orbiting in the cold and the dark leftovers from the planet formation process that swept through the solar system 4.5 billion years ago. Pluto wasn't an anomaly, it was a pioneer, the first Kuiper Belt object humanity ever found. We just didn't know it at the time because we discovered Pluto 62 years before we knew the Kuiper Belt existed. And that discovery recontextualized everything. Suddenly, Pluto wasn't the odd ninth planet. It was the first member of a new class of objects, a representative, an ambassador from a previously unknown population. But the discovery that truly challenged Pluto's planetary status came in 2005. Astronomer Mike Brown, working at Palomar Observatory in California, found an object in the Kuiper Belt that was larger than Pluto. Not by much, only about 27% more massive, but definitively larger. They named it Eris, after the Greek goddess of discord and strife. A fitting name because Eris created discord in the astronomical community. If Pluto was a planet, then Eris should be too. And if we were going to call Eris a planet, we'd probably have to call several other large Kuiper Belt objects planets as well. Makemake, Haumea, Quaoar, Sedna. The list could grow to dozens. Either we accept that the solar system has dozens of planets, most of them small, icy, and barely studied, or we redefine what a planet is. The International Astronomical Union chose redefinition. In August 2006, they established 3 criteria for planethood. The object must orbit the Sun. It must be massive enough for its own gravity to pull it into a roughly spherical shape. And crucially, it must have cleared its orbital neighborhood of other debris. That third criterion was the sticking point. Earth has cleared its orbit. Jupiter has cleared its orbit. Even tiny Mercury, smallest of the traditional planets, has cleared its orbit. But Pluto hasn't. It shares the Kuiper Belt with thousands of other objects. Its mass isn't dominant in its orbital zone, so Pluto was reclassified. Not a planet, a dwarf planet, a member of a different category sharing space with Eris, Makemake, Haumea, and the asteroid Ceres. Many people felt this was unfair, a demotion. An insult to a world that had been part of our mental map of the solar system for 76 years. Some scientists still argue the definition is flawed. Alan Stern, principal investigator of the New Horizons mission, has been particularly vocal, pointing out that even Earth, Jupiter, and Neptune haven't truly cleared their orbits. They all have asteroids and other objects sharing their orbital space. But here's what the debate misses. The reclassification wasn't about diminishing Pluto. It was about understanding context. Pluto isn't less interesting because it's a dwarf planet. In fact, it's more interesting because it's not alone. It's part of a population. And studying that population tells us things we could never learn by studying one object in isolation. The Kuiper Belt contains information about the early solar system. These objects formed far from the Sun in cold, low-density regions, where planet formation proceeded slowly. Unlike the inner planets which collided, merged and differentiated into layers of core mantle and crust, Kuiper Belt objects remained relatively pristine. They're aggregates of ice and rock, loosely bound, never subjected to the intense heat and pressure that transforms worlds. They're archives, time capsules, preserved examples of what the raw material of planet formation looked like before planets formed. And they're diverse. Not all Kuiper Belt objects are the same. Some, like Pluto, are large enough to have undergone geological activity. Others are small, inert, unchanged for billions of years. Some orbit in neat circular paths. Others, called scattered disk objects, have highly elliptical orbits that carry them far from the Sun, sometimes hundreds of astronomical units before swinging back inward. Eris is a scattered disk object. Its orbit takes it as far as 98 astronomical units from the Sun, nearly twice as far as Pluto ever gets. At that distance, the Sun appears as nothing more than a bright star, not a disk. Just a point of light brighter than other stars, but not warm, not life-giving. Just there. and Eris has a moon, a small one named Dysnomia, just like Pluto has Charon. In fact, many large Kuiper Belt objects have moons. Haumea has 2. Makemake has 1. The presence of moons suggests that collisions were common in the early Kuiper Belt, and those collisions threw debris into orbit where it coalesced into satellites. Haumea is particularly strange. It's shaped like an elongated egg spinning rapidly, completing one rotation every 4 hours. That rapid spin, combined with a collision that stripped away much of its outer ice layers, gives it an elongated shape, unlike any other known object in the solar system. And it has a ring, a thin belt of debris orbiting around its equator, probably fragments from the same collision that created its moons. It's bizarre, wonderful, a reminder that the outer solar system is full of surprises. Another fascinating object is Quaoar, about half the size of Pluto. Quaoar has a moon named Weywot. But what makes Quaoar interesting is its density. Measurements suggest it's denser than expected for a pure ice rock mixture. That implies differentiation, separation of materials by density with heavier elements sinking to the center. But differentiation requires heat. Where did that heat come from on such a small, distant object? Perhaps from radioactive decay. Perhaps from tidal heating during interactions with other Kuiper Belt objects. Or perhaps Quaoar formed differently in a region with more rock than ice, giving it a composition unlike its neighbors. We don't know, and that's part of the excitement. Every new object we study raises new questions, reveals new possibilities, challenges assumptions. And then there's Sedna. Discovered in 2003, Sedna has the most extreme orbit of any known large object. Its closest approach to the Sun is 76 astronomical units far beyond the Kuiper Belt's outer edge. Its farthest point is an estimated 937 astronomical units. One complete orbit takes about 11,400 years. At aphelion, Sedna is so far from the Sun that if you stood on its surface, you could block the Sun completely with your thumb held at arm's length. It would be dimmer than a full moon seen from Earth, and the temperature would be colder than anywhere else in the solar system, except perhaps other extreme objects like it. Scientists don't fully understand how Sedna got into such an orbit. The prevailing theory is that a passing star billions of years ago, during the Sun's early days, when it was still part of a stellar nursery crowded with other young stars, perturbed Sedna's orbit, flinging it outward. Or perhaps a hypothetical Planet 9, a massive world lurking in the distant outer solar system, pulled Sedna into its current path. The existence of Planet 9 is still debated. Several distant objects, including Sedna, have orbits that seem to cluster in unusual ways, suggesting the gravitational influence of an unseen massive planet. But no one has found it yet. If it exists, it's out there in the dark too far, and too dim to see with current telescopes. Searching for it is like looking for a black cat in a dark room. Except the room is billions of miles across, and you don't even know if the cat exists. But the search continues. Because if Planet 9 is real, its discovery would rewrite our understanding of the solar system's architecture. It would mean there's another major planet beyond Neptune, hidden for all of human history waiting. Now, in 2019, 4 years after the Pluto flyby New Horizons encountered another Kuiper Belt object, Arrokoth. Originally designated 2014 MU69, Arrokoth is about 36 kilometers long, shaped like two spheres stuck together, what scientists call a contact binary. It's red, covered with tholins, and remarkably smooth, with almost no craters. Arrokoth is the most distant object ever visited by a spacecraft. At 6.6 billion kilometers from the Sun, it represents the farthest reach of human exploration. And its shaped two lobes connected by a narrow neck tells a story about how Kuiper Belt objects form. Scientists believe Arrokoth formed from two separate objects that gently collided and stuck together. Not a violent impact, but a slow, careful merge, like two snowflakes drifting together and freezing into one. That gentleness suggests the early Kuiper Belt was calm. Objects didn't smash into each other at high speeds. They drifted, touched, joined. It's a different story than planet formation in the inner solar system, where collisions were violent, energetic, world-shattering. Out here in the cold and the dark, things move slowly, patiently, building up through accumulation rather than catastrophe. And that calmness preserved information. Arakoth looks almost exactly as it did when it formed 4.5 billion years ago. It hasn't been melted, compressed, differentiated, or resurfaced. It's original, pristine, a fossil from the solar system's birth. Have you ever thought about what it means to be original? In a world where everything changes, where erosion and time smooth away all edges, where nothing stays the same, Arakoth is original, unchanged. A piece of the past still existing in the present, untouched by the billions of years that transformed everything else. And there are thousands more like it, waiting, silent, orbiting in the dark, holding secrets about the early solar system, about planet formation, about the distribution of materials in the primordial disk from which everything Earth, Jupiter, Pluto, Arakoth, and us eventually formed. The Kuiper Belt isn't the end of the solar system. Beyond it lies the scattered disk, where objects like Eris wander on highly elliptical orbits. And beyond that, the Oort cloud, a vast spherical shell of icy bodies extending halfway to the nearest star. Comets originate there, perturbed by passing stars or galactic tides falling inward toward the sun. Their ice is sublimating into glowing tails as they approach the warmth of the inner solar system. The Oort cloud has never been directly observed. It's too far too diffuse. But we know it exists because comets exist, and comets have to come from somewhere. So, the solar system isn't a neat, bounded structure with planets and then nothing. It's layered, textured, full of populations and regions, each with its own characteristics, its own story. And Pluto sits at the boundary between the familiar and the strange, between the worlds we've known for centuries and the worlds we're only beginning to discover. That's why Pluto's reclassification matters. Not because it diminishes Pluto, but because it places Pluto in context. It tells us that the solar system is larger, more complex, more populated than we thought. That there are thousands of worlds out there, each with its own geology, its own chemistry, its own history. And Pluto, by being the first one we saw up close, showed us what's possible, what these distant frozen worlds can be. It's not the 9th planet, it's the first dwarf planet we explored, and that's something far more profound. And so, New Horizons, having completed its mission, continued outward, leaving Pluto behind, carrying with it one final gift. On July 14th, 2015, at 7:49 a.m. Eastern Time, New Horizons reached its closest approach to Pluto. 12 minutes later, the spacecraft crossed into Pluto's shadow. For a brief moment, the sun disappeared behind the dwarf planet. And in that darkness, New Horizons turned its cameras back toward the world it had just visited, capturing something no human had ever seen before. Pluto at dusk. The image that came back, transmitted across 5 billion kilometers, traveling for 4.5 hours at the speed of light, is one of the most beautiful photographs ever taken in the history of space exploration. Pluto appears as a dark silhouette, a black circle against the deeper black of space. But around its edges, something glows, a thin, delicate ring of blue light. Pluto's atmosphere, backlit by the sun, scattering light into layers of haze that wrap the planet like translucent silk. It's ethereal, fragile, almost impossible to believe that something so beautiful could exist in a place so cold, so distant, so utterly removed from everything we know. And in that single image, all the data, all the measurements, all the scientific analysis condenses into something simpler. Something that doesn't need equations or explanations. Wonder. That photograph became iconic almost immediately. It was shared millions of times, printed in newspapers and magazines, projected onto screens in classrooms, planetariums, and lecture halls. Not because it taught us new physics or revealed unexpected chemistry, though it did both, but because it reminded us of something we sometimes forget in the pursuit of knowledge. That exploration is beautiful. That science at its best doesn't strip away mystery. It reveals deeper mysteries, more questions, more reasons to keep looking, keep wondering, keep asking, what else is out there? New Horizons spent only one day near Pluto, one day out of a 9.5-year journey. But in that day, it gathered enough data to keep scientists busy for years. The full data set took 16 months to transmit back to Earth, compressed encrypted sent bit by bit across the vast emptiness between worlds. And every week as new images arrived, as new spectra were processed, as new topographic maps were constructed, the picture of Pluto grew richer. Mountains made of water ice, plains of flowing nitrogen, a heart-shaped region that shouldn't exist, canyons on Charon that tell the story of a moon that once held liquid water beneath its surface, moons tumbling chaotically through space, colors that speak of organic chemistry unfolding over billions of years, an atmosphere that breathes, that changes, that might collapse entirely within a few decades as Pluto moves farther from the sun. It's not just data, it's a portrait, a biography, the story of a world written in ice and shadow and light. And here's something that often gets overlooked in discussions of Pluto's demotion. None of this would have happened if Pluto had remained the 9th planet. Not the mission itself. New Horizons was already in development before the 2006 reclassification. But the way we think about it, the context we place it in, by recognizing Pluto as part of the Kuiper Belt, by understanding it as representative of a larger population, we transformed the mission from visiting the last planet to exploring a new frontier. And that shift in perspective matters. It opened the door to missions to other Kuiper Belt objects. It legitimized the study of small icy worlds. It reminded us that size doesn't determine importance. Pluto taught us humility, not because it's small, but because it's complex. Because even a dwarf planet at the edge of the solar system has geology, atmosphere, moons, weather patterns, and processes we don't fully understand. If Pluto, tiny and distant, can surprise us this much, what does that say about the rest of the universe? It says we've barely started, that every answer leads to 10 new questions, that the more we learn, the more we realize how little we know. And that's not discouraging. It's inspiring. Because it means there's always more to explore, always another horizon, always something beyond what we can currently see waiting to be discovered by whoever has the courage to look. After Pluto, New Horizons continued flying. It's still flying now in 2025, nearly a decade after the encounter. It's in interstellar space, the region beyond the influence of the sun's solar wind, where the sun's magnetic field no longer dominates, where the environment is shaped more by the galaxy than by our star. It's traveling at about 14 kilometers per second, fast by human standards, but in the vastness of space, achingly slow. It would take New Horizons over 80,000 years to reach the nearest star, Proxima Centauri, if it were headed in that direction, which it's not. The spacecraft will drift, silent, alone, powered only by the slow decay of plutonium-238 in its radioisotope thermoelectric generator, producing electricity from radioactive heat. Eventually, in a few more years, there won't be enough power to run the instruments. The transmitter will shut down, the heaters will stop, and New Horizons will go dark. But it will keep moving. Forever, unless it hits something. 1 trillion years from now, long after the sun has exhausted its fuel and collapsed into a white dwarf, long after the Earth is gone, long after any trace of humanity has faded, New Horizons will still be out there, coasting through the void, carrying a record of the civilization that built it. And on that spacecraft, there's a small aluminum container. Inside it, some of Clyde Tombaugh's ashes, the man who discovered Pluto in 1930, scanning photographic plates in Flagstaff, Arizona, looking for Planet X. He died in 1997 before New Horizons launched. But in 2006, as the spacecraft was being prepared, mission scientists included a portion of his cremated remains, along with an inscription, "Interred herein are remains of American Clyde W., Tombaugh, discoverer of Pluto and the solar system's third zone." Adele and Muron's boy, Patricia's husband, Annette, and Alden's father, astronomer, teacher Punster, and friend Clyde W. Tombaugh, 1906-1997. It's poetic. A man who spent his life looking at distant worlds finally reached one, not in body but in spirit, not alive but present. A witness to the culmination of the search he began 85 years earlier. And there's something deeply human about that gesture, about carrying someone's ashes to the place they spent their life studying, about honoring not just the discovery, but the discoverer, about remembering that science isn't just data and equations, but people. People with families, with humor, with lives lived in service of understanding. Have you ever wondered what will remain of you after you're gone? What mark you'll leave? What echoes will persist? For most of us, it's small things. Memories in the minds of people who knew us. Photographs. Maybe a few objects passed down through generations, their stories fading with each retelling. But Clyde Tombaugh, his ashes are traveling through interstellar space. His name is on a spacecraft that will outlast civilizations. His discovery, that small icy world at the edge of everything, inspired one of the most ambitious space missions ever attempted. That's legacy, not fame, not recognition, but impact. The ripples you create that continue long after you're gone. And Pluto's legacy is similar. It changed how we think about the solar system. It revealed a frontier we didn't know existed. It showed us that distance doesn't mean dead, that small doesn't mean simple, and that the edges of things are often the most interesting places to look. Before Pluto, we thought we understood the architecture of the solar system. 4 rocky planets, 4 gas giants, and that was it. A neat, orderly structure, predictable, complete. After Pluto, we know better. The solar system is messier, richer, full of populations and regions we're only beginning to map. The Kuiper Belt, the scattered disk, the Oort cloud. And beyond that, the interstellar medium, and eventually other stars, other systems, other worlds that might be as strange and surprising as Pluto proved to be. Exploration doesn't end. It expands. Each discovery opens new territories, new questions, new reasons to keep going. And maybe that's the real gift Pluto gave us. Not the data, not the images, but the reminder that there's always something beyond the horizon. Always another mystery. Always a reason to look up at the night sky and wonder, what else is out there? Since the New Horizons flyby, over 200 scientific papers have been published analyzing the data. Researchers have studied everything from the composition of Pluto's ice to the dynamics of its atmosphere to the orbital mechanics of its moons. Graduate students have written dissertations. Textbooks have been rewritten. Our understanding of dwarf planets, of ice chemistry, of planetary geology in extreme cold has been transformed, and we're still learning. The data from that single day in July 2015 will be analyzed for decades. Future scientists with better tools, with different questions, will return to the images, the spectra, the measurements, and find things we missed. See patterns we didn't notice. Ask questions we didn't think to ask. That's how science works. Not in sudden revelations, but in slow accumulation. Each generation building on the work of the previous. Each discovery revealing new complexities, new subtleties, new mysteries. And 10 years from now, 20 years from now, when we finally send another mission to the Kuiper Belt, to Eris perhaps, or Haumea, or one of the many large objects we haven't yet visited, we'll compare what we find there to what we learned at Pluto. We'll ask, is this similar, different? What does that tell us about how these worlds formed, evolved, changed? Pluto won't be alone anymore, not in our understanding. It will be part of a family portrait, the first one we met, but not the only one worth knowing. And maybe someday humans will visit in person, not in our lifetimes, probably not in our children's lifetimes, but eventually. If we survive long enough, if we keep building, keep dreaming, keep pushing outward. Imagine standing on Pluto's surface, the sun, a bright star providing no warmth, barely any light. The ground beneath your feet, nitrogen ice colder than anything you've ever touched, hard as stone. Charon hanging in the sky, enormous, never moving, always there. The stars visible even at midday because the atmosphere is so thin it barely scatters light. The silence absolute, broken only by your own breathing, your own heartbeat. What would you think standing there? What would it feel like to be 5 billion kilometers from home, farther than any human has ever traveled, looking back toward the inner solar system, where Earth is just a pale blue dot, lost in the glare of the sun? Would it feel lonely, or would it feel connected, part of something larger? A member of a species that started in caves and tide pools and eventually made its way to the edge of the solar system, driven by nothing more than curiosity and the refusal to accept that some questions are too hard to answer. That's what Pluto represents. Not a planet, not a dwarf planet, not a point of data or a target for a mission, a destination, a challenge, a reminder that the universe is vast and strange and full of places we've never been, things we've never seen, wonders we've never imagined. And every now and then, we get to see one up close. To visit a world that's been waiting in the dark for billions of years, patient and silent until the day a small spacecraft, built by curious beings from a distant world, came flying past cameras, clicking instruments, measuring, gathering light and data to carry back across the void. That day was July 14th, 2015, and the world we visited had a heart made of ice mountains made of water, an atmosphere that breathed, and 5 moons dancing in the darkness. We called it Pluto, and it changed everything. Thank you for drifting with us through this journey, for staying through the cold and the dark, through the science and the poetry, through the numbers and the stories. Pluto is still out there, still orbiting, still breathing its thin atmosphere into space, still painting itself red with tholins, still turning slowly, always showing the same face to Charon, locked in an endless dance that will continue long after we're gone. And somewhere far beyond it, New Horizons is still flying, carrying a piece of the man who discovered Pluto, carrying the dreams of everyone who worked on the mission, carrying the message that we were here, that we looked, that we cared enough to send a spacecraft 5 billion kilometers just to see what was there. That's humanity at its best, curious, brave, willing to spend a decade traveling through darkness just to see something beautiful. And there are more stories waiting, more worlds to visit, more mysteries to unravel, more quiet nights where we can drift together through the cosmos, learning, wondering, remembering that knowledge isn't about having all the answers. It's about asking better questions. Sleep well, dream of frozen hearts, and when you wake, look up at the sky and remember there's a world out there with mountains of ice breathing thin air into the dark, waiting patiently for the next visitor to arrive. Good night.